of your presentation. Please.
Ага. Я спасибо большое, Валентин, за приглашение выступить с докладом. Я очень рад. И я помню, я посетил вас в Харькове несколько лет назад. Как я сказал раньше, сегодня утром, эта поездка и город Харьков мне очень понравился. И я надеюсь, что возможность будет посетить вас в Харьков как можно скорее после войны. И несколько студентов от вас, от Харькова, работали со мной в моей группе и защитили кандидатскую диссертацию, как, например, Мария Кайдаш. И я очень рад видеть вас сегодня. Ну, мы говорим на английском о химии. Еще раз спасибо большое. Today I would like to talk about relatively, my first project in the, first, how can I navigate? It's a little bit slow. Let's see. It's a moment.
Problem with your presentation?
Yes, at the moment I have the problem that it doesn't react.
Презентация не листается.
Maybe I will stop and start it again.
Okay, please try it.
Okay, just the presentation mode. Normally I can do it with the arrow, I thought, to navigate from one to the other. Let's see. Otherwise yes, now it works. Okay, good. Okay, just a few words about Rostock. Rostock is located at the Baltic Sea in the northeast of Germany. As you know, Germany was divided country. And I am maybe last member of the last generation, I mean, of the period of the Cold War. I did my military service actually in '88, 1 year before the, the end of the separation of the two parts of Germany. Rostock is a small city, but a quite old city. It's very old, actually more than 800 years. Or not 800, but more than 750 years. And the University of Rostock is also a very old one, actually more than 600 years. It's one of the oldest in Germany. Do you hear me well? Okay. This is just a picture of the central church. Maria Mascha knows the church, I think. And this is a medal which shows the emblem of the university, the process of the foundation of the university. We have 15,000 students, 9 faculties, and more or less all subjects. We have also interdisciplinary faculty, which is a relatively new one. And this is our building for the one of our buildings of the chemical department. Actually, my office is located here in the second floor, and we have also the Leibniz Institute of Catalysis, which is also part of our university. Okay, we are interested in the development of catalytic reactions and heterocyclic chemistry, let's say using building block chemistry. And the chemistry I like to talk today is one of my first projects as in the independent research, which we started in Göttingen. Actually, we can use dianions as synthetic building blocks. It is known for many years that 1,3-dicarbonyl compounds can be deprotonated not only one time, but 2 times. And this offers a possibility to functionalize the terminal rather than the central carbon atom of the dicarbonyl system. And also are known so-called masked dianions. These are, in a sense, electroneutral equivalents of dianions containing these silyl-enol ether moieties, the so-called bis-silyl-enol ethers. These are also known or were known for many years based on the work of Takan Chan, for example, in Canada. And these compounds can be prepared in 2 steps by silylation and additional silylation, let's say deprotonation of the silyl-enol ether and addition of trimethylchlorosilane again. And these compounds are more or less stable, let's say, but you need to take care. They are sensitive against moisture. At higher temperature, they undergo a rearrangement, the silyl migration, to give this type of compounds, which are also nice, but not that useful anymore. And these compounds, these bis-silyl-enol ethers, behave like dianions. So the highest nucleophilicity you have in the terminal carbon atom, not at the central carbon atom. These compounds you usually use in Lewis acid catalyzed or Lewis acid mediated reactions. And our idea was to develop cyclisation reactions of dianions and of masked dianions. This sounds to be very simple, but it's not, because dianions are highly charged compounds, very strong nucleophiles, and they can also not only react as nucleophiles, but also react as base. Therefore, you may have side reactions, eliminations instead of substitution, or even reduction because they are so electron rich, or decomposition and polymerization. And our concept was now to use a proper reactivity tuning of the dianion and the electrophile. And the second strategy, to use the so-called masked dianions, the 1,3 bis-silyl-enol ethers. And I would like to guide you a little bit to show you some results. And for example, we developed a new synthesis of butenolides. So we developed the first cyclisation of 3 1,3-dicarbonyl dianions, which can be generated directly from the 1,3-dicarbonyl compounds by using 2 equivalents of LDA or 1 equivalent of sodium hydride and then N-butylicium. But the direct cyclisation of this dianion with compounds like diethyl oxalate or oxalyl chloride doesn't work. You have decomposition. The dianion is simply too reactive. But to make a long story short, we were successful by using the bis-Weinreb amide, which is shown here. You may know the concept of Steven Weinberg. He used this type of, well, for simple carboxylic acid derivatives, this type of moiety, which prevents decomposition and overaddition of nucleophiles. And with this, we were successful and obtained the gamma-alkylidine butenolide. In red, you see the dicarbonyl compound. And you see the cyclisation proceeded regioselectively via the carbon and the oxygen atom. So this carbon and the oxygen atom. So the first attack took place at the terminal carbon, as expected, because it's a dianion, and then via the oxygen rather than the carbon atom. And this is based on the so-called Baldwin rules and the, let's say, orientation of the orbitals. And the exocyclic double bond is formed with very good E-selectivity, simply because it is a thermodynamically more stable compound. Well, it is a kinetically controlled reaction, but the thermodynamically controlled product is formed faster. Or alternatively, we have maybe an equilibration after formation, but we can only isolate the E-configured isomer. And the reaction is quite general, so you can use various different types of dianions with different substituents, amides, or in the central carbon of the dianion, we can have a substituent, or something like butyroacetyl gamma butyrolactone to get this type of compound. And in nearly all cases, these compounds are configurationally stable with respect to the exocyclic double bond, except from this one, with this ketone, the methyl group. Here, we observe broad signals and a mixture at 20 degrees and coalescence upon heating. So you see, in this case, we have a equilibrium, but in all other cases, we are in the region of the slow exchange on the NMR time scale. Usually always E configuration, except from this type of molecule when we have a substituent located at the terminal carbon atom of the 1,3 dicarbonyl unit, simply because of the steric effect of the substituent. Then we developed, let's say, a variant of this process using the bisilanyl ether. This means mask dianion. Now we have a very weak nucleophile. Yeah, it is an electroneutral compound, and we use now a very strong electrophile. Before it was opposite. We had a very strong nucleophile and a very weak electrophile, but now it's the opposite. And to activate oxalyl chloride, we add TMS triflate as a Lewis acid, and we get the same type of product. The same product, actually, like in the dianion reaction, but this process is much more general. In case of the dianion methodology, we had a number of restrictions with regard to the substitution pattern, but this is more general. So here you see, for example, this type of molecule having an oxygen in the ring. This was not available from the dianion methodology, simply because you could not generate the dianion with a methoxy group in present due to the pi donating effect of the oxygen atom. And also bicyclic products like these were not available by the dianion methodology. Then we tried to apply also this chemistry to the synthesis of some small natural products, and it is known that gamma-alkylidine butinolides occur in a number of natural products, like, for example, mushroom. And this is known by work from Pettenden and Steglich, for example, Wolfgang Steglich in the University of Munich. So we applied our cyclisation reaction, obtained this butinolide, and then modified the hydroxy group, which comes originally from the oxalyl chloride, by a triflate and subsequent Suzuki coupling, and obtained this compound. And this one, then we were able to deprotect regioselectively this methoxy group in the presence of the other one by using BBR3. This is an SN2 type process. And the regioselectivity can be explained by the beta leaving group ability of this, let's say, vinylogous acid as compared to this one here, to the phenolate. So we were lucky at the end to get the pinastric acid then in a single step at the end. And our methodology was also used by other researchers, for example, by Charles Mioskovsky in Paris, to prepare norbidione A, or let's say an analog of that, which is the compound present in mushroom, which enriches also cesium ions. And this was the reason why, after the accident in Chernobyl, it was not recommended to eat mushroom, because the mushroom or the natural product enriches cesium ions, also the radioactive isotopes. And to study that, Mioskovsky used our methodology to get the butinolide, and then obtained let's say, this compound, and then did a number of chelation experiments. And we applied also the methodology to the synthesis of nitrogen heterocycles, and it is possible just to replace the oxygen by a nitrogen simply using an amine in acidic media. So we obtained that, and this could be transformed to puckylamide A, which is a natural product. This we did not do ourselves because it was known in the literature. The selectivity, when we have a substituent here at the nitrogen, by steric effects, we have the E configuration. If we have a hydrogen, the Z configuration, because of formation of an intramolecular hydrogen bond, in this case also. Okay, then we hydrogenated the compounds also, and in a racemic way. So hydrogenation under standard conditions of the butenolide gave the gamma-lactone with high diastereoselectivity. The reason is that after the first hydrogenation, which takes place in the exocyclic double bond, the second hydrogenation takes place from the sterically less encumbered side of the molecule. Therefore, we get the cis configuration, but a racemate. We can use the hydroxy also to, let's say, to reverse a configuration. And we can, if we have a hydrogenation of this compound having an additional substituent in the ring, only the exocyclic double bond is hydrogenated. This molecule is a little bit similar structurally to vitamin C, but it's a racemate. All compounds are racemate. And then we tried also to get enantiomerically pure compounds by enantioselective hydrogenation, but this was not possible. Unfortunately, the EEs were very low. But in collaboration with Professor Uwe Bornscheuer at the University of Greifswald, where I worked at that time, he is an expert of enzymatic kinetic resolution reactions. And so he used our compound and used commercially available lipase, but he also in his group develops by evolution methods new enzymes. It was possible to have an enzymatic resolution and get the enantiomerically, or isolate the enantiomerically pure compound on a small scale, let's say 20 milligrams. But it was possible to do it. Then we also try to use these type of molecules, which are a little bit longer, let's say have a longer chain. You see an additional double bond in the silyl ether, and here we get the corresponding butenolide as expected, cyclization via the terminal carbon and the neighboring oxygen atom, but as a mixture of EZ isomers. And the reason is probably that for the EZ selectivity, the presence of the carbonyl group in this position here, let's say in the center, is important. Here we don't have it. And this is probably the reason why we lose the stereo control. Okay. In case of substituents, we have only one isomer. And if we have a 1,3,5 tris silyl ether with an additional oxygen atom here in place, then we regain the selectivity of the exocyclic double bond and exclusively obtain the E-configured product, this one here, but let's say as a mixture of keto-enol tautomers. I only show the keto tautomer. Then we also studied this type of building block, which you can consider as a electroneutral equivalent of a dianion of a carboxylic acid, right? If you have, I mean, you can generate dianions of carboxylic acids, and you can also make these type of, let's say silyl ketene acetals from in 2 steps. And then we developed cyclization with oxalyl chloride and get this type of maleic anhydrides having hydroxy and a substituent in this position. And this is also quite general, and you can get a number of different substitution patterns, more or less 20 or 25 different derivatives. Just I show you here, maybe a few. The yields of these reactions are never great, yeah. So usually moderate, but we never get extremely high yields in these reactions. So 90%, it's very rare, but very often moderate, too good maybe. And another process I would like to show you. Maybe let's have a look at this silylated compound. This is like a bisilyl enol ether, where you have here a single bond rather than a double bond. It is nothing else than a product of an aldol reaction, let's say of ethyl acetate with acetic aldehyde, right? Aldol product, which is then bisilylated or silylated 2 times. So you can consider that as a silylated aldol. And we developed a cyclization. Here you don't need a Lewis acid. You get the corresponding product, which is formed by cyclization via the oxygen atom and the central carbon atom of the silyl enol ether. And the product is like structurally a little bit related to a isoascorbic acid derivative, having the hydroxy next to the carbonyl group. And this is also quite general process. Many products we prepared. Let's say I didn't prepare anything, students prepared. And let's say, but we have always racemates, yeah, because we start with a racemate. And then we try to use also an enantiomerically pure starting material. And we don't lose the absolute configuration during the reaction. This is maybe the important news. So we can get the product enantiomerically pure because the absolute configuration is preserved. And this was proven by chiral HPLC method. So you see, the oxalyl chloride is a favorite molecule. I like it. And oxalic acid derivatives, because actually this was a project of my habilitation. And so always products are somehow oxygen heterocycles, butenolides, maleic anhydrides, lactones, different type of molecules. And now this was also reviewed, 2 review articles which are focused on silyl enol ethers, bisilyl enol ethers in general, these masked dianions, and their application to oxalyl chloride in a Zynlet account article, 2006. And now I would like to talk a little bit about the formation of other heterocycles and the use of other electrophiles rather than oxalic acid derived electrophiles. And this was also reviewed with regard to the dianion chemistry in 2004 chemical reviews and related to alkylidene tetrahydrofuranes, which play a role in this chapter in tetrahedron. So it is known that the reaction of free dianions with halides, let's say, is not that easy as it seems. Because especially if you use 1,2 dihalide, let's say a 1,2 distance, yeah, between the halides, for example, like 1,2 dibromoethane, you get a reduction rather than a substitution, and no cyclization at all, and not even a substitution, because the single electron transfer is faster than the substitution. So this is a typical example of a reduction, which is very fast. So you get the dimer of the dicarbonyl compound. And this is known already from 1976. So the question was, how can we realize or make a cyclization from a 1,3-dicarbonyl dianion and a 1,2-dihalide? That was not known at that time, although it is a very simple idea. And the answer is not that difficult. You simply have to shift from 1,2-dibromoethane to bromochloroethane. So you replace one bromine by a chlorine. Then at a low temperature, you add the compound and then you heat it, reflux in THF, and you get the corresponding alkylidene to alkylidene tetrahydrofurane, exclusively as the E-configured isomer. And the formation of the product proceeds by attack of the terminal carbon atom of the dianion to the bromide, and cyclization upon heating via the oxygen atom. These are again the Baldwin rules, attack onto the chloride. And so actually a number of products can be prepared. It's quite general, 20 or 30 derivatives, always these alkylidene tetrahydrofuranes. And then we try to use also 1,4-dibromobutene, which has an additional double bond. And here we have in principle two possibilities, 1,4 cyclization to give a 7-membered ring, or 1,2 cyclization, which involves a SN prime reaction. And this takes place. Actually, we get in the cyclization this product. It's a formation of a 5-membered ring. Again, a 2-alkylidene tetrahydrofurane with a vinyl group in position number 5. And this comes from the double bond. So actually the terminal carbon atom of the dianion attacks the bromide. It's an SN2 reaction. And then the oxygen attacks the neighboring carbon, an SN prime reaction, and shift of the double bond. And then we get this type of compound. And in collaboration with Professor Uwe Bornscheuer in Greifswald University, we also realized enzymatic resolution of this. In this case, when we have the vinyl group, initially the product is formed as a mixture of E and Z isomers. But upon standing, slowly, and in the presence of acid, much faster, we have a rearrangement to only give the corresponding E-configured product. We can also use this type of dianions where the ester or the ketone is replaced by a sulfone. So these are beta-ketosulfones. You can generate dianions from this type of molecule. Similarly, as we had ester group instead of the sulfone, and makes a cyclization. Then we get this product here, a bicyclic product. Again, a racemate, but the product is formed with very good diastereoselectivity. Exclusively this relative configuration in the 1,3 distance. And this can be explained by consideration of the open-chained intermediate after the first attack. In one case, we have a less favorable interaction between the double bond and the bridgehead hydrogen. And in the other case, which leads to the product observed, we have the other, let's say, conformation. A product is isolated. Not the yield, not very high, but it's okay. So, and then this product undergoes a rearrangement, a palladium catalyzed rearrangement in presence of palladium 0 catalysts. You know the maybe the Barry Trost chemistry. He worked a lot on let's say pi allyl palladium complexes, and in this case happens something similarly. If you treat this compound here with a palladium catalyst, you have a cleavage of this carbon-oxygen bond to give a pi allyl palladium complex. And this pi allyl palladium complex is an electrophile which is attacked subsequently by the central carbon atom of the monoanion, which is formed as a leaving group. And from this carbon atom, we observe a recyclization to give this bicyclic product. So it is actually an isomerization reaction. And what is interesting and important, we don't lose the relative configuration. Probably because the pi allyl palladium complex is configurationally stable, which is maybe not expected, because at elevated temperature, it is known that pi allyl palladium complexes can undergo isomerization reactions, but in this case, it's not. If we had an ester rather than a sulfone, we do observe an isomerization and get both isomers. Yes, so this slide shows a little bit different reaction again, where we use now epibromohydrin as an electrophile in the reaction with the free dianions. We again get alkylidene tetrahydrofuranes and with a hydroxymethyl group in the 5 position. These compounds can be formed in principle by 2 ways. Possibility number 1, attack of the carbon atom onto the bromide to give this intermediate, and then attack of the oxygen to the epoxide, formation of this intermediate, which then, upon addition of water, provides a product. In this case, the reaction works very well only if we add lithium perchloride to, let's say, to the reaction mixture. And because of the presence of lithium, we believe that because of this reason, initially we exclusively get the Z-configured isomer. But this slowly, upon standing or faster in the presence of TFA, trifluoroacetic acid, and undergoes isomerization to give the E-configured, the thermodynamically more stable E-configured isomer. Alternatively, the product can be formed by attack of the dianion to the epoxide and subsequent cyclization via the oxygen atom. And this is the reason why we lose the absolute configuration in case that we used the enantiomerically pure epibromohydrin. We get a racemate probably because both reaction paths take place. But the reaction itself is quite general. If you let's say don't want to prepare enantiomerically pure compounds, you can get this type of compound, and also many different substitution patterns of the dicarbonyl compound are in principle tolerated. But to get enantiomerically pure compounds, to start with enantiomerically pure epibromohydrin, it's not so good. Then we studied, maybe, okay, this we skip. Maybe let's see this one, which is related process. Yeah, we use now an epoxide in the reaction with a masked dianion, and use now titanium tetrachloride for the activation, stoichiometric amount of titanium tetrachloride. So it's not a catalytic reaction. Starting with the cis-configured epoxide, we get trans, and vice versa. Probably because in the first step, we have an SN2 type process with inversion of the configuration to give this intermediate, and then attack of the oxygen, which is derived from the epoxide, onto the double bond with retention of the configuration. So therefore, we have only one-time inversion and one-time retention. Therefore, the relative configuration changes from trans to cis. At least this is our that what we think. And the advantage of this reaction is that functional groups are tolerated. So just a few minutes ago, I showed to you the reaction of the free dianion with epibromohydrine, where we obtained the hydroxy in the side chain. Now, we preserve the bromine in the side chain. So the reaction is highly hemoselective because of the mechanism which I just showed to you, right? So attack onto the sterically less encumbered side of the epoxide, and then cyclization via the oxygen atom onto the dicarbonyl system, and the bromide remains unattacked. Therefore, this process is quite useful to, if you are interested, to prepare alkylidene tetrahydrofuranes with a functional group in the side chain. And if you have alkylidene tetrahydrofuranes, you always also have the tetrahydrofuranes, because we can hydrogenate, we did this also, we can hydrogenate the exocyclic double bond, and also with a very good, let's say, diastereoselectivity. And we use that also together with the chemical company as a building block for drug discovery, because tetrahydrofuranes are useful also to prepare as a scaffold, let's say. And the advantage of this process is that if we use enantiomerically pure starting material, and there are enantiomerically pure epoxides either commercially available, or you can get them by catalytic processes. For example, the Jacobson epoxidation. The absolute configuration is preserved. So, for example, if we use enantiomerically pure epichlorohydrin, do the cyclization, we get the enantiomerically pure product. Because of the mechanism, this center here is not involved in the mechanism, and therefore we preserve the absolute configuration. Then we studied also the employment of alkylidene tetrahydrofuranes as building blocks in further functionalization reactions. So you can lithiate and add additional groups in this position in the exocyclic double bond, or it's possible to make a dehydrogenation with DDQ to get furanes, or palladium catalysis. It's possible, or hydrogenation. Of course, we get racemates, but then in collaboration with Uwe Bornscheier, enzymatic resolution, again, then the enantiomerically pure compounds. And in this case, Professor Bornscheier and his group used esterase Est56. And this is an enzyme which is not commercially available and also not native, but which was developed in his group technically by an evolutionary process, just for the optimization of this specific reaction. The disadvantage is that you always have to optimize again for each individual substrate. And this slide shows, let's say, shows a ring transformation reaction to transform alkylidene tetrahydrofurane having this type of anisole moiety into a benzofurane with a remote bromide, simply by treatment with BBr3. Everything is cleaved, and we get a recyclization to give the corresponding product having a remote bromide, which you can then functionalize further later on. And yeah, a number of derivatives were prepared, also some a little bit strange compounds, for example, like this one here, having chloride and bromide next to each other. So and it's not that easy to get the compounds in a different way, because yeah, we follow simply a, let's say, a cyclization ring cleavage strategy. Just to summarize this, so I mean, we were interested in the synthesis of alkylidene tetrahydrofuranes by using free and masked dianions, and then these compounds are building blocks for the synthesis of a huge variety of different different molecules. Now I have to ask one question. The normal duration of the presentation, Valentin, you said is 40 minutes. Yeah, what is the usual time? I mean, this is depends up to you. So I think maybe 5 minutes more. Would that be okay? Or
Yeah.
what is the usual?
Yeah, okay, no problem.
Yeah, this is up to you, let's say, because it's maybe a little bit too long, the presentation, and this is a disadvantage. So therefore, just not to make it too long, maybe just we will skip quite many things and maybe just go a little bit further. I show you one example for the synthesis of Kaba cycles.
Yes.
And which is shown in here, because I know that, for example, from enamine, you know, enamine in Kiev, I visited also Kiev, and also we had good interaction also with enamine company. They prepare also fluorinated building blocks because they are drug-like compounds. And we developed many 3+3 cyclizations using these masked dianions. I give you one example. You can get this known in the literature. You can react vinyl ethers with this anhydride. This normal anhydride doesn't work, but if you have the CF3 group, which is very reactive one, you can have this building block in only one step. And then we developed a 3+3 cyclization. So this means this carbon, terminal carbon, and the central carbon of the bisyl null ether undergo cyclization, and we have an attack in this carbon and this carbon. So 1,3 dinucleophile with a 1,3 dielectrophile. Before it was always a 1,2 dielectrophile. Now it is a 1,3 dielectrophile. Here we have a reduced selectivity always via the 2 carbon atoms because we form benzene derivatives. And we form 6-membered rings rather than 5-membered rings. The advantage of this, let's say, building block strategy is that the reaction is regioselective. So the CF3 group is only located next to the ester because the first attack always proceeds by a conjugate addition to the double bond. And we can use also silyl and null ether fluorinated, silyl and null ethers. We can also have different substituents and so on. So just to show that these type of reactions exist. And this reaction is also maybe interesting for you because it's a cyclopropane. You can get it in one step. And this 1,1-diacetyl cyclopropane undergoes a cyclization with the bisyl null ether in the presence of titanium tetrachloride to give this type of salicylate. So always salicylates we have, with a chlorinated side chain, which comes from the cyclopropane, and the chloride comes from the Lewis acid. So cyclization to give the spiro compound, cleavage by the chloride, because this is highly reactive, and formation of the product. And this is also quite general process. And regioselective process also. And this is also maybe interesting. This example, when we have a non-symmetrical compound with a methyl or with methoxymethyl, you see. And the first attack occurs in this position, probably because of acylation. So it's a regioselective process. And we can combine this also if we have a protective group like benzyl cyclization, cleavage with hydrogen, and then this oxygen, which comes from the cyclopropane building block, undergoes nucleophilic attack to the chloride, which comes from the titanium tetrachloride and the cyclopropane, and we get this type of molecule. And then you can play around with this one and also prepare a number of derivatives to get this type of molecule. And then we were also lucky because we managed also to isolate the intermediates by using the free dianions. And these compounds show activity against blood cancer, against HL60 cells. Maybe not extremely strong, but also selective activity, which is probably due to the alkylating effect. I mean, the cyclopropane is a very good alkylating reagent, and maybe it alkylates the DNA of cancer cells, but we don't know the mechanism. The compounds are structurally a little bit related to the illodine natural products, which show a much better even anti-cancer activity. Okay, so this was maybe an example for the synthesis of Kaba cycles. And then maybe just as a last chemical slide, or maybe two more chemical sites I will show you. Maybe this is the first one. We were interested also in chromones. And, you know, in Ukraine, we have excellent scientists which are interested in chromones also. And we studied the reaction. I mean, in Rostock, we also studied a lot the chemistry of chromones, and everything started with the reaction with bisalylinolysis. So you can activate chromone by addition of TMS triflate. You get this molecule, the beryllium salt, which is then attacked next to the oxygen atom, and you get this intermediate. And the interesting part is now, if you add now triethylamine, you get a domino reaction, which is a retromichael aldol lactonization reaction to give this type of lactone. So in the first step, the carbon-oxygen bond is cleaved, retromichael reaction, then an aldol reaction, aldol condensation, attack of the central carbon atom onto the carbonyl, and then a lactonization. And yeah, this was also interesting to develop new fluorescence dyes, blue fluorescence dyes. It had a technical application, but it was not useful for any technical, let's say, real technical application, but at least we got some fluorescence measurements done. The idea was originally for this project to develop a new blue, let's say, color for traffic signs. In the highways in Germany, you may know the traffic signs are always blue. I don't know, I know in Ukraine they are maybe green, I don't remember that, but in Germany these are usually blue. And the idea in the project from the European Union was to develop new traffic signs with blue color, which has a fluorescence, in order that the driver, and usually often people drive very fast, can see them more rapidly. But therefore we studied the compounds, but I mean, obtained the project, but it was too costly to get this type of application done. And this is the last slide, which I just wanted to show you. This slide shows that sometimes, if all your chemistry fails, you can be still lucky. Because the idea was to prepare these vinyl chromanones. The idea was to study palladium chemistry with this type of molecule, because we had the idea it would be interesting to form palladium, parallel palladium complexes and do some interesting reactions, but everything failed. But the compound itself showed some activity, not very strong, but some activity against bacteria. And then we optimized that and came up at the end with, let's say, these molecules, which are highly active against multi-resistant strains, also the methicillin-resistant Staphylococcus aureus, which is, let's say, often a problem in hospitals, because if people get infected in hospitals, very often multi-resistant strains can be a problem. And the activities are very high. And then we did a patent in collaboration with biochemists. Also the mechanism of, or the mode of biological action was also studied. Unfortunately, no company took it over, because usually they are not interested to buy patents. They want to do their own things, but then it was at least an interesting result for us. Okay, so this I wanted to show you. I like very much dicarbonyl compounds because it was for, I mean, gave interesting results at the beginning of my academic career, and all this chemistry followed us for many years, let's say but then we, at a certain time, then if you have published so many things in one area, it's maybe then also time to say goodbye and to stop it, because it's getting more and more difficult to get things published. Even if you think, oh, this is great, but the reviewers think, oh no, we have seen so many things like that from you, so we don't want it anymore. So then maybe in about 2008, 2009, then we stopped that. And I'm very grateful to the students who did all this work. So many PhD students from us worked in the field of free and masked dianions and did their PhD thesis, also diploma or master and bachelor thesis in this topic. Our group is very international one. So not only from Ukraine, I think we had 5 or 6 students who got the PhD in Rostock with me. We had also students from many other countries, for example, from Pakistan, from Syria, Iraq, but also from South America. We have a strong collaboration with Cuba, for example, and in Germany with Hungary, for example, but very strong collaboration also with Armenia. Many students worked with us, PhD students, but also I think now more than 50 students obtained their master's thesis, because every year we invite 2 or 3 students from Yerevan State University to work with us for 6 months during their bachelor or master thesis. The defense is always in Yerevan, but the results are usually produced here, and then we publish together with the colleagues and friends in Armenia. And so international group, and thank you very much again for the invitation today. And of course, I'm also shall be glad to answer questions if you have questions.
Thank you very much, Peter, for a very nice talk and for interesting and rich chemistry. So you can ask your question, please, in German, English, Spanish, French, Russian.
I try to understand it. Thank you.
Dear colleagues, do you have any questions? I don't see you.
Десенка had.
Десенко, Сергій Михайлович, будь ласка.
Дякую. Dear Professor Langer, first of all, I should like to say many thanks for you, from me, from all of us, not only for lecture, but for your help for Ukraine, for Ukrainian scientists in that time. And your lecture is a large help for us, because we now, most of us are disconnected from real science, and you gave our air of science after some weeks of other problems in our life. I have a small questions about science. First of all, small questions about thermodynamic and kinetic control. Slide near beginning of your lecture, common scheme of thermodynamic and kinetic control with where Coulomb derivatives cyclizations anion in 2 different isomers. That slides approximately near beginning of lecture. No.
Early.
One of the first slide. Later. Later, next maybe. Next. Oh,
Previous.
reverse.
Yes, this one.
Oh, this one. The simple and questions. Is it possible to observe to rearrangement of kinetic product into thermodynamic product? And the second part of these questions is it possible to observe obtaining thermodynamic products in other conditions?
Okay. Yeah, first of all, thank you very much for the question. Yes, for me it's also maybe related to the first part. Honestly, I'm very sad about the situation, and I also the refugee center where I worked as a volunteer is also not a nice place. I registered there just because I thought it would be good maybe to help and maybe to translate, and then, but I didn't expect to be called. But then the city called and they said, yes, okay, and can you come in 30 minutes, 6 buses will arrive. And Rostock is not a big city, a small city. Then I went and 10 buses came. And this was really at the beginning, this hall is like a Wystavka, like fair hall, was, let's say, more or less empty, and then it was full, and it was quite chaotic. And then the problem is I have the tendency to talk a lot with people, but my duty was to register also the people. And then I talked with the people because also they wanted to talk to me also, and this was so it was for me very touching, and it was very, yeah, also very sad, and then but it was good. So actually, it was good to then to be able to help at least a little bit. But it is so unfortunate that, and I hope that soon everything will stop, and then of course we will continue always our collaboration. And I really like to visit you again in Kharkiv and Kiev and Lviv. I also visited. Still, their situation is still a little bit better, but I'm sure that everything will again also will be fine, and we will always collaborate together, and the student exchange we will always continue, and this for sure. Okay, now maybe the answer to the question, chemical question. Yes, in the very first moment, with regard to the exocyclic double bond, we get Z, which is kinetically controlled, and then upon standing, it is E configuration. But often, already during column chromatography, this rearrangement takes place. And therefore, very often we never see the Z configuration. This is with regard to the exocyclic double bond. And then maybe the question, cyclisation, the formation of a butenolide or formation of a, let's say, a 5-membered cover cyclic ring. This cover cyclic rings, 5-membered cover cyclic rings, we never observe. Probably because, again, of stereoelectronic control, the Baldwin rules. And these compounds cannot undergo a rearrangement. So the gamma-alkylidine butenolide, we also tried to transform somehow by isomerization to a 5-membered ring, but this doesn't work. So it seems the butenolides are themselves so stable that at least they cannot be transformed to the cover cyclic products.
Thank you. If it's possible, a second question.
Sure, of course.
Questions about enantiomer selectivity of dehydrogenization, some later. If it's possible, a more detailed about these results, about condition of, yes, about condition of this reaction, influence of conditions on enantiomer selectivity, so on.
Let's say like this, okay, the hydrogenation we can not get in an enantioselective way using, let's say, chiral ligands, something like that. But these enzymatic resolution,
yes,
the basis for that is that the ester group of one enantiomer is more rapidly cleaved than the ester group of the other enantiomer, because the enzyme has a chiral environment and recognizes one enantiomer. The condition, let's say the use, or let's say which enzyme is suitable, depends very much on the structure of the substrate. So in this case, lipase amano PS, this is a lipase. Commercially available lipase is suitable, I would say, by good luck, for this substrate. If you have a little bit different substrate, for example, without the methoxy group, it doesn't work anymore, or not so good. Therefore, the optimization has to be done for, individually for each individual substrate. The reaction conditions are typical in a phosphate buffer, let's say neutral condition, aqueous solution, together with toluene. So it is a two-phase system. And reaction times relatively long, 25 degrees. So it is, let's say, typical for this type of enzymatic processes. But I'm not an expert in that. This is the work of my colleague, Uwe Bornscheuer, and the student, Annette Kirschner. She was a diploma student in Greifswald, and we had a joint supervision by Professor Bornscheuer and me. Here you see in the table that the EE depends from the reaction time. At the beginning, if you stop the reaction too early, we can separate the two compounds because we have the acid and we have the ester. They have a different polarity. And for one of them, actually, we get the high, let's say, selectivity already very soon. And for the other one, with the time. So the time plays a role also for the reaction. Yes. And a practical issue, by the way, in order to improve the separation of these compounds, the polarity is still different, or already different, but still maybe it is useful to do a methylation in order to facilitate that. But this is only a practical aspect. The scale of the reaction is 100 milligrams starting material.
Thank you.
Thank you.
Thank you very much. Do you have other question? Please talk because I don't see you. Yeah, Maria, будь ласка.
I am so glad to greet Professor Langer. Of course, it's a big pleasure for me to see your face because the last time we just wrote to each other emails, and it's a great chance to see you.
Thank you.
And of course, I want to say that Professor Langer is a person who did so many things for many foreigners, for so many young people. Professor Langer has opened the gate to the life.
Thank you. That's my duty. Thank you very much. It was, for me, it's a great pleasure to work with the students. And also, I was very lucky to have you in my group, and also the other students from Kharkiv. Actually, I was very lucky with the students who joined my group.
Yeah, sure. A lot of people have got possibilities in their lives, and also they are trained. Personally, I can say with this situation, what is now in Ukraine, lives of all people has changed. But personally, for me, this change is easier to follow because we have been trained when we have moved to Rostock, to Germany, to your group, and all other changes which have been happening during whole our lives are easier to accept psychologically. So thank you a lot for this great life school, I would
Thank
say.
you. And I just want to say to that, my parents were, I mean, quite old when I was born. So actually both of them were, when the Second World War ended, my mother was 16 and my mother was 14. Mm-hmm. My father, he was a refugee in 1945. They lost everything because they had to flee the area of, let's say, Gdansk area, Danzig. And not Gdansk, it is Wrocław, Wrocław. And the city then for my mother, Hanover, this city was destroyed 90%, nearly completely. You can even see it nowadays because you only see new buildings. And this was also something which, when I was a child, let's say 6 years, then I asked my parents, okay, how was it? My father never wanted to talk about this. My mother, she talked about that, and therefore, for my own parents, I mean, it was many Germans at that time were also refugees. Therefore, I'm very, it's so difficult to understand this really. You only understand this if you talk to the people, for example, with the families I just, who arrived in Rostock, how it is, for example, that you have to leave your home, maybe only with one rucksack. And this was so sad and so difficult. Yes, and I just wanted to say that from my parents, I mean, they had this type of war experience also, although it is so long time ago. Maybe nobody still remembers that, but yes, my parents at least. And so yes, we will always we will continue our collaboration, and I think also the collaboration in the science, and therefore I'm also so happy about this, your series, that it continues, the chemical discussions, let's say, and the possibility to come together at least in an online way also. It is important because we are not only interested to prepare compounds or develop new reactions, but I think the most important part of our work in the university or the Academy of Science is also to make relations between the people. These relations are very important, and I think they will last for a long time, and also will be stronger than all the destruction and horrible time of the war. It will be, this is an important aspect of the science in general, I think.
Yeah, I hope we all will survive and will continue our work. And I also had a small chemical question. It is about biological activity. It was a slide near to the end of the presentation.
Yes. Stop. Yes. No, this was with
It
regard.
was about hormones.
Yes. Yes, this one, I think.
Yeah. Yeah, I wanted to ask you, Professor Langer, if it is the first example of compounds, was it the first batch where you have checked the biological activity?
Let's say no.
Like historically in your group.
Maybe yes. This I don't remember. Yes, it could be, because in the beginning we were not so much interested in that, and I also did not know anybody who, let's say, worked in this field. But then I had a colleague in Greifswald University who was interested in that, and we set up a collaboration. And this was Michael Lalk. And this was maybe the starting point for that.
Yeah, because biological activity was so much developed since this time in your group. In each work, there were some parts connected to biological activity.
Yes.
So it's interesting to know that this was a starting point.
Yes, yes, that's true. That's true. And this is always, but we never do any biological studies ourselves. It's always in collaboration, and therefore it's also good to know people. And for example, okay, this was related to bacteria, and it's always good to maybe to get this type of contact. To promote the biological studies. I think, yes, it's interesting for us. But unfortunately, we also very often don't do that, because it depends very much also on the PhD student. Very often, if they have a friend or a friend of a friend, then things are going more rapidly than if the professor has to establish that, because the student has to have an interest also on his own. Then usually things go very well, and this is at least my experience.
Yeah, thank you. It was very interesting, actually.
Thank you.
My question also about biological activity. You synthesize a lot of biological active compounds or analogs of biological active compounds. What do you think about your chemistry generally? Is it possible to implement your chemistry into pharmaceutical industry as a method of synthesis of biological active compounds, or not? Because low temperatures, stability of intermediates, and so on.
Yes, well, I would say this is difficult to say. Maybe it would be a good idea to do it in a systematic way and in a more broader sense. Because if you do a lot of screening in many areas with many compounds, then the probability to get an initial hit is high. But in our case, it's more random. It is not so systematic. Therefore, I would say theoretically, you are absolutely right. It would be a good idea, not only this project, but maybe also other projects, to study biological activity in a systematic way. But for that, you need then many collaboration partners in many biological areas. And then you need to have also students or a person who takes care of that. That means that we prepare a little bit more of the material. Then also to make a library, really. I mean, we have a library, but this is only maybe a small quantity, just in case that an analysis, something is missing. But we need maybe a library, or to create a library of all compounds, and also an electronic database for that, and then offer it maybe to industry or to whatever with some initial screening results. But this would need for sure, maybe an additional person or one person who only takes care of that and organizes that. And this person I don't have, let's say, because we have a lot of teaching also to do. But it would be a good idea to have it and to do it.
And what do you think? Is it possible to scale up your reactions, your chemistry for industry application?
This depends. Sometimes we had collaboration with industry. For example, we had just to show you something which I just because of the time I did not show you. Okay, so we developed, for example, this one, a synthesis of highly substituted benzophenone derivatives. This was a project, I mean, also related to chromone, but formyl chromone. This was a project which was funded by the industry, by a pharmaceutical company close to Berlin. And there we did a screening, and also these compounds are out of a list of about 40 derivatives, the best with the best activity against activity as selectin antagonists. This important, let's say, selectins play an important role in the early state of inflammation process. So the idea was to develop new drugs against inflammation. And in this case, we also studied the scaling of reactions. And the upscaling is not always easy, and it's not like this that it can be done for all reactions which we develop. Very often reactions work very well, maybe for 1 millimole scale or less than 1 millimole. But if you want to do it and maybe let's say 50 or 100 millimole scale, then you face problems. For example, simply because of the dilution, you need higher amount, for example, of solvent, which is not practical anymore or very costly, and things simply don't work in a higher concentration, for example. So to make it's in some cases, for some projects, we developed successfully also upscaling. Upscaling means maybe to prepare 5 or 10 grams of a compound, yeah, but not a kilogram scale. But also again, only when we had a collaboration with companies and when there was a need for that, really.
I understand. Thank you. So, dear colleague, do you have other questions to?
Recorded.
No? If you don't have a question, thank you very much, Peter, for very nice talk and for your... okay, Irina.
Yes, thank you. Nice to meet you, Professor Langer. My name is Tkachenko Irina. I'm grateful for you about this very interesting presentation. And I have a question. Please slide with antibacterial activity resistant Staphylococcus aureus. Yes, золотистый стафилококк. Yes, I want to ask you about methicillin-resistant Staphylococcus aureus. Yes, it is measured from millimeters. Can you explain it for me? What does it mean?
This is
only millimeters.
Yeah. Okay, this is only the let's say initial screening. This is the diameter of the region in a plate where you have, let's say, the bacteria, which is then inhibited by a specific amount of the compound. So this is like a first screening, which is always done to have a first impression of the antibacterial activity under standardized conditions. Mm-hmm. And then usually the next step is to study the minimal inhibitory concentration, which is then a quantitative value. And this is given below. These are these micromolar per milliliter.
Okay.
So the millimeter is just the diameter of the inhibition zone in the first initial screening.
Okay, thank you. And I have also one more question. Maybe did you test these compounds on toxic activity?
Yes, this was done also, and this we didn't do ourselves. This we did in collaboration with Professor Hecker in the University of Greifswald, who is a specialist in this field. And the compounds have an selective activity against the bacteria. So it's not like this that cells die when you treat, let's say, but this was this was done, but we did not carry it further. So it is still the quite initial thing. I mean, the idea of this collaboration was then, this I did not show, with Professor Hecker, to see also where in the cell the compound attacks exactly and why it is active. But it is not like this that that these compounds are ready to use. This is still far away from that. So it is still very, very initial state. So what has to be done is then, let's say, activities that maybe to study that also in vivo, for example, and but all that was not done.
Okay, thank you.
Thank you.
Thank you. Professor Desenko also has a question.
So many questions about biological activity provocate me to continue this theme. Questions is, did you do interest in molecular modeling of biological activity, not only antibacterial of these compounds, docking and so on?
Yes, at that time when we did this project, not, but later, and for example, in the thesis of Maria Kaidash, we had to collaborate on completely different type of molecules and methodology, let's say, which have nothing to do with this topic. We have a collaboration with Professor Jamshed Iqbal in Pakistan, and they study phosphatase inhibition, for example. So let's say inhibition processes. And in this context, also docking studies are carried out. And this is useful to have it because it gives you an idea why and where, I mean, the compounds are active.
Some information may be useful for you or your colleagues. Now in Hamburg, as a refugee, situated our postgraduate student Svetlana Kovalenko. Now he didn't work anywhere, only travel in Hamburg. The term of his postgraduate education was concerned with docking, with molecular modeling. Maybe her interesting for you, for our colleague, maybe for our colleague from Hamburg. Now she is situated in Hamburg.
Yeah, okay, that's a good idea. Maybe she can write me an email.
Yes, I think we will connect you with Svetlana Kovalenko. Maybe, yes, it's a good idea to establish this type of collaboration now because she's in Hamburg.
We began this investigation only last years, but have some interesting results, and maybe specialists in this region may be interesting for you or your colleagues.
Yes, that would be good. Thank you.
I don't know about presence of Svetlana Kovalenko in this conference. If she is present,
No, she is not here.
no, maybe no possibility.
Yes, I think you're right.
Okay, no problem. You can, maybe she can simply write me an email and then we can figure it out.
Okay, I'll send you the email of Svetlana. Yeah, okay. Okay, dear colleague, do you have other question? No? No. Oh, here are some explosions in Kharkiv. It's quiet from the morning, but now, okay. Thank you very much again, dear Peter, for your presentation and for your talk and for your help to Ukrainian citizens in Germany.
С удовольствием. Спасибо вам.
Yes, we will be in touch in the future, and I hope for future collaboration, deep collaboration between our organization, between our laboratories, laboratory of Professor Desenko and you. Okay, thank you.
Thank you very much for the invitation again. And I want to draw your attention also on the possibility that in Germany there exist specific programs also for Ukrainian, let's say, scientists in danger. So this is something which you can also find in the internet, which gives some possibility for funding also. So just maybe to know that something like this exists.
Yes. So, see you for the next meeting in Kharkiv, I hope.
Yes.
Шановні колеги, я сподіваюся, ми будемо продовжувати наші семінари. І якщо у вас є ідеї, кого ми можемо запросити, я наразі думаю, що ми будемо спілкуватися з професором Варником. Топік його доповіді, скоріш за все, буде інший. Це буде якраз докінг і фармацевтичний скринінг. Тобто це квантова хімія. A little bit other topic. Okay, so I stop